I'm going to start off with a nice easy one, the derivative of 3 to the x. Now this may be one of the differentiation rules that you have memorized, but it actually comes from logarithmic differentiation. So it's really nice as one of our examples. Now there's a nice step-by-step process here. So your very first step is to take your function and rewrite it as the statement y equals. So now I've got y equals 3 to the x. The next thing that I want to do, step number 2, is to apply a natural logarithm to both sides. And the reason that I choose the natural logarithm is because it's the easiest one to differentiate. And I get to pick any log that I want to apply to both sides. Now remember those property of logarithms. This is what saves the day here. I've got a power and I can bring the power out in front. So I've applied the logarithm and I'm simplifying with those properties. So I end up with the natural log of y, nothing to change there. On the other side, I get x times the natural log of 3. My next step, step number 3, is to apply the derivative d dx. Now, if you haven't seen my video yet on implicit differentiation, take a look down below. The link is there and it will take you through exactly what you need to know, but we're going to use a little bit of implicit differentiation here. So I'm going to apply d dx to both sides of my statement. So d dx of the natural log of y is equal to d dx of x natural log of 3. Now y is a function, and notice that x is our variable of integration. So when I take the derivative on the left-hand side, I need to take the derivative of the natural log of y, but the natural log is my outer function, and y is a function, so it is my inner function. As I apply d dx, I end up with 1 over y, but y is a function, so I follow that with a chain rule, and I get y prime. Again, this is implicit differentiation. Take a look for that video link down below. On the other side, I can pull the natural log of 3 out in front, so I get the natural log of 3 times the derivative of x, but the derivative of x is just equal to 1. So I have 1 over y times y prime is equal to, the derivative of x is equal to 1, so it's equal to the natural log of 3. Now my goal is to find the derivative, and my derivative is this guy. So I need to multiply both sides by y. So I end up with y prime is equal to y times the natural log of 3. But right now this answer is implicitly defined. I don't want it implicitly defined. I want y prime as a function of x. So my final step is to go back to that very first statement and replace y. So I end up with y prime is equal to y, which is 3 to the x. So 3 to the x times the natural log. And that is our answer. So we took our function, y equals, we applied the natural log to both sides, we used some properties of logarithms to simplify, and then used implicit differentiation to run that derivative through our statement. Finally, we solved for y prime. Let's take a look at a second example. In this one, I've got the derivative of x to the x squared. I don't have just a nice differentiation rule, so instead we are going to use logarithmic differentiation. Basically, I'm going to be freeing this x squared with one of my properties. Step number 1, just like we had before though, is to take our function and write it as y equals, so that's going to be y equals x to the x squared. Step number 2 is to apply a natural log to both sides and simplify using any properties. So I've got the natural log of y is equal to the natural log of x to the x squared. Now I can apply that property since I have a power inside, and I can pull that power out in front, and I end up with the natural log of y is equal to x squared times the natural log of x. Step number 3 is to apply our derivative to both sides of the equation. So I'm going to apply d dx to the left-hand side, to the natural log of y. y is a function, so I need to make sure I follow any derivative with that with a y prime. On the other side, I'm applying that d dx, but everything on the other side is the variable of differentiation, so ln x. Okay, so what do we get? Well, the derivative of a natural log is 1 over whatever we've got inside the natural log, but that was a function y, implicit differentiation, so I follow that with a y prime. On the other side, I've got a product, so I need to do a product rule here. This is f and this is g, so I'm going to apply my product rule, so I need f prime g plus f g prime. Okay, so what do we get? Let's take the derivative of x squared first. That's going to be 2x times, I leave the natural log alone, plus, let's reverse the order. I'm going to leave x squared and multiply that by the derivative of natural log, which is 1 over x. I can actually simplify this. I can cancel this x, and I'm left with just an x. Let's rewrite what we've got before we go on to our next step. So we've got 1 over y prime is equal to 2x natural log x plus x. Next, I need to multiply both sides by y. I'm solving for y prime. So we can call this step number 4. We want to solve for y prime. So we're going to solve for y prime equals. So I need to multiply both sides of this equation here by y. I'm almost at my answer. I have y prime is equal to, but I multiplied that side by y, and I also have everything else. So I've got let's put the parentheses, 2x natural log x plus x. Last step, step number 5, is to go back to how you defined y in the very beginning and replace y right here. Right now my derivative is defined implicitly, but I really want it to be y as a function of x, or I should say my derivative as a function of x. So finally I can write y prime is equal to, I'm going to put y in, that is x to the x squared, and I'm just going to leave all of this. You could certainly multiply it through 2x natural log of x plus x, but this is our answer. Let's do another one like we saw at the very beginning, where we want to avoid a product rule, a chain rule, and a quotient rule. So in this one, I've got the derivative with respect to x of all of this stuff. Now, I could simplify the numerator, I could, but I would still be left with needing to apply a quotient rule and a chain rule. Instead, I am going to apply properties of logarithms to simplify this. So let's go ahead and go through our steps. So step number 1, I'm going to take that function and rename it y. So y is equal to x parenthesis x squared plus 1 divided by the square root of x plus 1. Step number 2, apply a natural log on both sides and some properties. So I get the natural log of y is equal to the natural log of, here's where all those properties are going to come into play, x squared plus 1 divided by the square root of x plus 1. Now there's no property to apply on the left-hand side. Everything's going to happen on the right-hand side here. So first of all, I've got a quotient here. So I'm going to apply that property that says that the natural log of a quotient is the difference of natural logarithms. So this is equal to the natural log of the numerator, x squared plus 1. I'm not going to multiply that through. I want you to see how to apply another property, minus the natural log of square root of x plus 1. Now the square root is actually a 1/2 power. So instead of having the square root, I'm going to put a 1/2 power. That's going to allow me to use another property of logarithms. Okay, so I've got a couple more properties to apply. I have a product in the first natural log. I can rewrite that one as a sum. So this is going to be the natural log of x plus the natural log of x squared plus 1. I can bring that 1/2 out in front because it's a power, so minus 1/2 natural log of x plus 1. Okay, so I've got everything ready and I'm ready to apply my derivative. Let me just scoot things over a little bit. So I gave myself some more room and I'm going to put that natural log y that lived on the left-hand side and I'm ready to apply my derivative all the way through. So I'm going to just kind of squish it in here so I don't need to rewrite everything out. So d dx and then a d dx right here. So here we go with the derivative. Now the derivative of the natural log of y is a function. So I end up with 1 over y, a chain rule gives me y prime on the other side. Next I've got the natural log of x. This is my variable of differentiation, so no chain rule needed, 1 over x. In this next one, I've got x squared plus 1. I do need a chain rule here. I'm going to do 1 over whatever's on the inside times the derivative of what I've got on the inside. Well, what I've got on the inside is x squared plus 1, and the derivative of x squared plus 1 is 2x. Finally, I can leave that negative 1/2. And I'm going to take the derivative of the natural log of x plus 1. That's 1 over that value that's on the inside, which is x plus 1. I do technically have a chain rule, but it would just be the derivative of x, which is equal to 1. I can clean things up a little bit here, not a ton of cleaning up to do, but I do need to bring my y over to the other side. So as I'm cleaning this up, let me put things back in white. I end up with y times 1 over x plus, I can write this as 2x over x squared plus 1 minus 1 over, let's move that 2 through, 2x plus 1. All I've got left to do is to bring my y back. Now I need to go and grab my y from way up at the very beginning of the problem. Here is my value y that I defined at the very beginning. So I'm going to go ahead and take this and put it in for y in my final answer, and then I'll be done. Let's go back down to the bottom. So finishing this off, I've got y prime is equal to y. Here comes y. It was x times the quantity, x squared plus 1, all divided by the square root of x plus 1 times what I've got there in the square bracket. So 1 over x plus 2x over x squared plus 1 minus 1 over 2x plus 1. Now that's our answer. This is one that you could have absolutely have done using some simplifying, a quotient rule and a chain rule, but logarithmic differentiation is just another method to go here. I've got one last example for you. I wanted to finish with one like this because in this one we have to use logarithmic differentiation. We didn't actually have to use it in the last example. But in this one, I don't have a choice because it's an x to something in terms of x. So I'm going to start with step number 1, which is to write y equals that function, so cosine x. Step number 2 is to apply that natural log on both sides. And this is where the magic happens, right? Because this is where I'm able to kind of free that cosine of x and bring it out in front. So I end up with the natural log of y is equal to cosine of x, that's a cosine, times natural log of x. Once I've got it simplified, I'm ready for step number 3, and that's to differentiate. So I'm going to apply d dx to both sides of my equation here. d dx cosine x, and I'm going to need a product rule here times the natural log of x. Let's move this up so we can continue with the derivative. So on the left-hand side, the derivative of the natural log, super consistent. I am getting 1 over y times y prime every single time. On the other side, though, I do have a product rule. So I've got f times g. So let's work through that product rule. The derivative of cosine is negative sine. So I get negative sine x times g, natural log x, plus, I'm going to leave f alone, so that's going to be cosine x, times the derivative of g, the derivative of natural log is 1 over x. Next, I need to bring that y and multiply it on the other side. This is where I'm so close to having my answer. So y prime is equal to y times, I'm just going to rewrite what I've got there, negative sine x times the natural log of x, plus, let's write this as cosine x divided by x. All I've got left to do is to take my definition of y, there it is, my original function, and put it into my answer. So y prime is equal to my function y, which was x, to the cosine x, times what I've got there in the parentheses. So negative sine x, natural log x, plus cosine x divided by x. Get some practice. The process is the same, but you do need to know those properties of logarithms, the chain rule and implicit differentiation. A lot goes into these problems, but I know you're going to get there. Take a look at the next video that I've got here. It's going to help you as you keep learning some more calculus. Thanks so much for watching.